Log on, tune in, find out. Another good idea from Cambridge.
And also from the Southampton Statistical Sciences Research Institute of the University of Southampton.
Thank you very much. Good morning. Today we'll introduce two new families of second-order equivalent estimation split plot designs. One is based on subset designs and another is based on supplementary difference set designs. This is a joint work with Harrison Makaria and Professor Peter Goss from the University of Antwerp. So during this presentation, we will see what is a split plot experiment and which model is suitable for data from split plot designs. Also, we will discuss the ordinary least square and generalized least square equivalence estimation property. We will describe our construction method, which is based on subset designs and on supplementary difference set designs, and we will provide several examples. We will give two lists with our results. One list contains the designs from subset designs, and the second list contains the designs from supplementary difference set designs. In the list, also we present the D and I efficiencies of our designs, and also for two cases, we will construct the fraction of design space plots. And we will end with some discussion. So now, industrial experimentation often involves one or more restrictions on the randomizations. So in these situations, one or more experimental factors are not independently reset for several runs. For these reasons, the observations are separated into groups. In these groups of observations are called whole plots. And inside these groups of observations, some factors are held constant, while others are set independently. So a factor that is held constant is called a whole plot factor, while the other factors are called subplot factors. And usually the levels of the whole plot factors are levels that are hard to change. So we have two separate randomization, the randomization of whole plots, which gives rise to the whole plot error, and the randomization of runs, which gives rise to the subplot error. In this work, we work with the second order response surface model for quantitative factors. So we have linear, quadratic, and two-factor interaction effects in our model. So in matrix notation, the model can be written in this way. Y is the vector of the responses. X is the model matrix, which contains an intercept, the main effects, the two-factor interactions, and the quadratic effects. Beta is the parameter vector. Z is a matrix with elements 0 and 1, which assigns the observations to the groups. So the element ij is equal to 1 if the observation I belongs to the whole plot J, to the group J. Gamma is the vector of the random effects of the whole plot, and epsilon is the vector of the random errors. For the random errors gamma and epsilon, we assume that are mutually independently normally distributed with zero mean and variances sigma gamma square and sigma epsilon square respectively. So the variance covariance matrix for the model is given from this matrix V. So in general, the split plot designs requires the use of generalized least squares to estimate the model. The problem is that the generalized least square estimator demands the estimate of the variance components sigma gamma square and sigma epsilon square. And this usually is done by the method restricted maximum likelihood method. But this method is still not implemented in some statistical software packages for industrial experiments. So this explains why some experimenters develop various methods for constructed split plot designs for which the ordinary and generalized least squares estimators produce the same point estimates. So here, we have the ordinary least square generalized equivalence condition, which is given by this equality. Here we have the ordinary least square estimator, and here the generalized least square estimator. And an alternative expression is given in this row. The ordinarily square, generalized square condition for second-order split plot designs is discussed first in Letzinger, Myers, and Lenter in 1996. Gauss and Vanderbroek showed that a lot of fractional factorial design, two-level factorial designs and fractional factorial designs guarantees this equivalent estimation property. Vining, Kowalski, and Montgomery, and Parker, Kowalski, and Vining introduced a new class of second-order equivalent estimation designs, which construct by modifying central composite designs and box banking designs. Gauss reports a lot of instances in which a d-optimal design is also an equivalent estimation design. And Macquarie and Gauss introduced an algorithm in which it's a column-wise exchange algorithm with which algorithm can construct d-efficient equivalent estimation designs. So now that we know what is a split plot experiment, we can continue with the construction method. First, we will start with the construction method that is based on subset designs, and then we will continue with the construction method that is based on supplementary difference set designs. So the subset designs are designs that are used in completely randomized experiments and are introduced by Gilmour in 2006. These subjects are constructed from all the combination of the level of the factors that appeared in the 3-power m design. So each subject SR contains the run that have r different factors acting at their high or low level, meaning that they have -1 or 1 level, and the m minus r remaining factors acting at their mid level, so with level coded by 0. So these designs have very attractive properties. They can estimate all the main effects and two-factor interactions independently. Also, they're factor-wise balanced, meaning that the estimate of the variant, meaning that all variances of the estimate for the main effects are equal. All the estimates of the variance of the quadratic effects are equal, and all the estimated of the variances of the two-factor interactions are equal. And also, they are designs with good projective properties. And special case of subject designs are the central composite designs and the box banking designs. So here we can see the 4 available subjects that we take for the 3 factorial design. The subject S3 contains all the runs that has the factors at the high or the low level, meaning -1 or 1. The subset S2 has the runs that has 2 factors at their high or low level and 1 factor at their mid level. The subject S1 is the subject of the axial points, meaning that exactly 1 factor has a non-zero value. And the subject S0 is a singleton and contains the center point. So the first step we need to take in order to construct our design is to sort the runs within every subject SR in increasing order of the whole plot factors. In this way, we obtain whole plots of different size, so that have orthogonal subplots. So we have to split this group into smaller ones in order to obtain whole plots of equal size. Some general remarks is that the subplot designs must be orthogonal to the whole plots in order to maintain the equivalent estimation property. Also, the axial runs for the subplot factors should be kept together when the subject S1 that we saw before is used. The axial runs for the whole plot factors need to be replicated in order to obtain balanced designs with whole plots of equal size. And all designs involving the center run must have the center run replicated in order to make, for the same reason, to have balanced designs. So for the 4 subjects that we saw before, the first step is to arrange the runs according to the first column of each subject, which is the column of the whole plot factor. From this subject, we will construct an equivalent distribution split plot designs with 1 whole plot factor and 2 subplot factors. So after we arrange the runs, we can see that in subjects S3 and S2, we have whole plots of size 4. So if we consider 4 as a whole plot size, we can construct the 3 following designs. The first option is to consider only subject S3 and S2, and in this way we can obtain 5 whole plots of size 4. Here we can see that no run is replicated in this design. In the second design, we consider runs from subject S3 and S1, and now we can see that we use these axial points, so we have to replicate it 4 times in order to obtain whole plots of size 4. And again, we will have 5 whole plots of size 4. The third option is to use subset S2 and S0. Here we have the center point that should be replicated 4 times, and now we will have 4 whole plots of size 4, so in total 16 runs. A remark is that the option 1 and 2 has no runs that reminds a central composite design or a box banking design, and are more suitable for cuboidal design region because they contain the vertices of the unit cube, while the third design is more suitable for spherical design region and is similar to a box banking design. The second family that we used in order to construct our equivalent estimation design is the supplementary differential designs, again designed suitable for completely randomized experiments that are introduced by Kukuvinos and al. The original designs involve 2 parts, a factorial part in which each run has 1 factor acting at its mid-level, and m-1 factors are set at either -1 or 1, and 2m different axial points at a distance a. The value of a is determined because these designs has a target to be rotatable designs. So here we can see a supplementary differential designs with 4 factors and 40 runs. Here we have the factorial portion of the design, in total 32 runs, because the vector 0, 8 and 0, 2 are 8 and 2 dimensional 0 vectors. And each of the first 4 runs is a 2, 4 minus 1 fractional factorial design with 1 column replaced by 0. So here in total we have 32 runs. And here this vector is the vector with elements +1, +a and -a. So we have in total 8 runs. Again, as exactly in the subject designs, in order to construct the equivalent estimation designs, we rearrange the runs of the factorial portion and of the axial portion in increasing order of the whole plot factor levels. And again, the subplot designs must be orthogonal to the whole plots in order to maintain the equivalence estimation property. So, in this construction, the axial runs for the subplot factors form a single whole plot. If necessary, the axial points are repeated in order to obtain a balanced design. And in this construction, we did not use the axial points corresponding to the whole plot factors. Again, these designs have the same attractive properties as the subject designs. The difference with the subject designs is that from this construction method, we obtain designs that are more appropriate always for the spherical design region. So, for the design that we saw before, this design, we can obtain an equivalent estimation split plot designs with 2 whole plot factors and 2 subplot factors by First, rearranging the runs of the factorial portion. So in total we have 32 runs, and we rearrange the runs in ascending order of the two first columns that we will correspond to the whole plot factors. So in this way, we obtain 8 whole plots of size 4. From the axial portion and from the initial 8 points that we have in the design, on the supplementary differential design, we will use only the axial points of the subplot factors. So we obtain one more whole plot of size 4. So in total, 9 whole plots of size 4. And now we will continue with our results. By this construction method, the d-efficiencies that we report in the table is given by this rate. X is the model matrix of the equivalent estimation design, and X-opt is the model matrix of the d-optimal design. Also, we report some relative I-efficiencies, which given by this ratio. The I-efficiencies that we report is with respect to the d-optimal design, and X here represent the cuboidal or the spherical design region. This design seeks to minimize the average prediction, this criterion seeks to minimize the average prediction variance, so it may be more appropriated for response surface designs that are concentrated to the prediction. So in this table, we can see the designs that we construct from the subset designs. The first column is the total number of runs. The second column, the number of whole plots. The third column, the number of whole plot factors. The fourth column, the number of subplot factors. Here we can see the region for which each design is more appropriated. So from the subset designs, we obtain designs that are maybe more appropriate for spherical or cuboidal design region. And in the last two columns, we see the d-efficiency and the I-efficiency of the design. The first three designs are the designs that we saw in the examples before. Some general remarks is that half of the design have more than 80% d-efficiency. Also, the equivalent estimation designs seems to be more I-efficient than the d-optimal designs. And this is a general remark. In general, we see some inverse relationship between the d-optimality and I-optimality. Also, we have some designs that are not so good in both d-efficiency and I-efficiency, like this design, the 48-run design. But these designs lacks of center points and axial points. So if we add a whole plot of center points, we can improve these values. The second table contains the designs that are constructed from the supplementary differential designs. Again, we can see the total number of runs, the number of whole plots, and the number of whole plot and subplot factors. Here we can see that we don't have the column of region because these designs are always suitable for spherical design regions. And again, we can see the d and I efficiencies. Some general remark is that these designs behaves better in terms of d and I efficiency than the designs that we construct from the subset designs. Again, we can see that there is an inverse relationship between the I efficiency and the d efficiency. Also, from the supplementary differential designs, we constructed non-balanced designs. The designs are non-balanced only because the whole plot that corresponds to the axial points has different size from the whole plots that correspond that we constructed from the factorial portion of the design. For example, we can see that these designs are not balanced, but we will not further analyze this property in this presentation. Also, we can see that this design, the 88-run design and the 204-run design is better in terms of d efficiency from the d-optimal design that we constructed by a column-wise exchange algorithm with 100,000 initial random designs. In the next two slides, we will see some fraction of design space plots. In the first graph, we use the 24 run equivalent estimation designs with 6 whole plots and 4 runs, 1 whole plot factor and 2 subplot factors. The solid lines correspond to our design, and the dashed line corresponds to the D-optimal design. So we can see that in general, our designs behaves better in terms of prediction variance, except for the 10% of the design region. In general, we can say that the D-optimal design has a smaller minimum prediction variance and a slightly smaller maximum prediction variance. In the second graph, we can see a 72-run design with 18 whole plots of 4 runs, 2 whole plot factors and 2 subplot factors. Again, our design is this one, and this is the D-optimal design. And here, clearly, we can see that the equivalent estimation designs that we construct from the subject design, this is a design from subject designs, and we for both graphs, we consider designs suitable for cuboidal design region, and we construct the graphs by assuming that sigma gamma square and sigma epsilon square is equal to 1. So in this design, in this graph, we can clearly see that our design behaves better than the D-optimal design in terms of prediction variance. So in this presentation, we show how to modify 2 families of second-order response surface designs in order to obtain equivalent estimation split plot designs. We offer to practitioners without access to advanced software an additional set of equivalent estimation split plot designs to choose from. And from the tables, we show that most of the designs are highly D and or I efficiency. We must say that both tables are by no means exhaustive because both class of subject designs and supplementary difference set designs that we use to construct them are infinite classes. So much more designs can be constructed by these classes. Thank you very much.
Are there any questions for the speaker? Perhaps first, I think.
So your I efficiencies are with respect to the D-optimal design, right?
Yes.
So you said that the designs were highly I efficient, but you didn't compare them to the I optimal designs.
Yes, we first consider the D-optimal criterion because we think that it's the most common criterion that is used to construct designs.
You can't really say that they're I efficient unless you look at the I optimal design.
Rosemary?
Those tables you showed us showing efficiencies, you surely must have been assuming some ratio between the variance components to construct that.
No, we don't assume because it's relative, the efficiencies and I efficiencies. But
your matrix V will vary depending on those coefficients.
Yes, we assume variance ratio equal to 1.
So you don't know whether that happens for a range of different ratios.
No.
But the relative high efficiencies are quite robust to the exact eta value, to the exact variance ratio.
Wasn't shown there.
I'm a bit worried about these people with the software that doesn't do weighted least squares. I think if they can't do that, I don't want them to run split plot designs because they're not going to get the right. As Peter said the other day, I think it was Peter anyway, emphasising the inference side of it. If they're not going to get the variance estimates, if they're not going to get the proper sums of squares out of their analysis, then isn't this a bit dangerous to be offering them these?
Yes, but at least this equivalent estimation property gives some
but
security.
you're not telling them anything about about the variances of their estimates, are you? I mean, the estimates are the same, but the variances are
comparing to the D-optimal designs, we do get an idea about the precision of the estimates.
Without estimating the two separate variance components.
Yeah.
You do, but the experimenter would. You do, but
They
the
can't.
experimenter would.
Yeah, that's true. Yeah. So yeah, basically what we're doing here is we extend the line of research that has been going on for quite a while, and it's sort of controversial in the sense that proper inference is not really available in these software packages.
These equivalent estimation designs do have other good properties, like the ability to estimate pure error and robustness to missing observations and things. Have you looked at any of these, or the split plot designs?
Robust? Sorry?
So some of the other good properties of completely randomized equivalent estimation designs, like robustness to missing values and ability to estimate pure error. Have you considered these properties?
These designs have all the good properties that the equivalent estimation designs that are constructed in the previous literature have, are constructed according to these designs. The only difference is that we use different families to construct them of designs.
Rosemary again.
Just that your reference there to the previous literature, you've actually omitted a huge amount of previous literature. George Stein, Simo Quintana and so on have published a lot about this property, but not under the name equivalent estimation.
Yes,
So
we
I-
concentrated.
Yes, so I would
on
recommend
this.
that you
Okay.
look at some of that literature.
Thank you.
I mean, your constructions give you nice designs, and one of the conclusions is that they have desirable properties in terms of the efficiencies. But I was just wondering, if you look at your tables and look at the number of runs required by the designs, is there perhaps a practical issue with those? I mean, that you may need quite a few runs to actually implement your designs.
Sorry? The number of runs, I think the important in split plot design is the number of whole plots, and not the number of runs. This creates the problem.
Another question.
Generally, we calculate D efficiency, taking relative efficiency, taking the ratio of two determinants, taking the denominator and the highest determinant. So there can be maximum value of 1. But you are showing more than 1 efficiency. Can you go back to the definition of D efficiency?
Yes, yes.
Yeah. Let me now go to the table where you have shown efficiency. The efficiency. Yeah, next slide. Yeah, the last one is 1.0583. So
Yes.
If we take relative D efficiency, taking the maximum determinant in the denominator, then maximum it can be 1.
Yes, but we construct the optimal design is constructed by a column-wise exchange algorithm with, in these cases, with 100,000 random starts. And it was really difficult to find a design that it's better than our designs in terms of D-efficiency. So this means that the design is really D-efficient.
So the absolute D-optimal design is not known. There are no theoretical results about what the theoretical upper bound is for the D-optimality criterion of a split plot design. So the best you can do is use software or a computer program to try to find the D-optimal split plot design for this particular situation. And it turns out that the software is not capable of finding the D-optimal design. The design that we constructed by hand is 5% better than the best one produced by the software. After 100,000 tries. So we really did our best. Any other questions or comments? If not, then let's thank this and the previous speakers again.